Our first examples with the discs and the washers were revolving around the x-axis, but as you can imagine, there's no reason we can't revolve around the y-axis as well. So I wanted to show you at least one animation of that and then go ahead and do a different problem. Let's see here. Here we're going to revolve this region, and this is this like guy here, y equals 1 minus x squared, but instead we're revolving it around the y-axis. So here, that's going to give us something like that. And we can see, let me turn that off. We can see if we go down here, what's going to happen. What you want to do, of course, is have your discs perpendicular to the axis of rotation. So it's going to sort of end up that way. And when we were rotating around the x-axis, they were going up and down, but here we're rotating around the y-axis, so they're going left to right in this sense, right? Or if you like, the discs are going up and down, or the discs are going left to right. However you want to think about it. The important thing, actually, is that you have the variables correct, okay? So the idea is the same, but you want to make sure that you're integrating with respect to the right thing. So let's go back and look at this problem real quick. This guy. What do I have? I got y equals 1 minus x squared in the first quadrant. So that's going to look like this. 1, 1, and I'm going to be revolving around here, right? So my disk, you know what, let me get rid of this. And you can just see me drawing on the board. So it's like, it's going to be this thing. And my discs are going to look like this. That's the terrible, terrible picture, but luckily we had a nice picture on the web. Now the important thing is we're going to do the same thing, right? We're going to do volume. It's going to be pi times the radius squared times d thickness of the disk. So, but here, because the disk is facing this way, your thickness is like this. So your thickness is going to be dy, which means I want my radius also to be in y. I want everything in y. Right here, actually, if I look at the radius is actually the x value, right? So I want to do this, x value squared dy, but I know it's dy. I have to have this in terms of y, okay? Well, but that's not that hard, right? Because I can always just solve for this. I take this equation, I can solve for it. I have x squared equals 1 minus y, and then x is equal to the square root of 1 minus y, right? And then all I have to do is put that guy in there. So I've got pi times the square root of 1 minus y squared dy. We could also have solved for x squared, but you know, oftentimes you won't have the x squared right there. You'll have to solve in some other way. So I just did it this way. The last thing I need to do here is my limits also have to be the y values because I'm integrating with respect to y. Here, of course, it's the same. You saw from the picture, it's 1, 0 to 1, or 0 to 1. So you can't really tell in this particular example, but it's really, my next one, we'll see that it is, oftentimes it's different. You want to have these guys be the y values because they have to match up with your variable of integration. Right, so then this isn't hard once I have this set up. I'm just gonna bang this through here. I've got 1 minus y dy. So I integrate, I get this. Evaluate from 0 to 1, that's a 2 down there, it looks crappy. So I've got pi times 1 minus 1/2 minus 0 minus 0. So I have pi over 2. So the area of that, the volume of that solid turns out to be pi over 2. Now I want to do one more where we're going around the y-axis, but with washers. So I don't have a pretty picture of that one, but we're just gonna, I always have to, I need to imagine, you're gonna have to sort of think about it and figure it out yourself. So this is most of the ones that we're going to have. They're not going to give you a picture. They're just going to tell you what the functions are, and you kind of have to figure it out yourself. So what we want to do is find the volume of the solid generated if we rotate the area from y equals x squared and y equals 2x in the first quadrant about the y-axis. Okay, so I need to kind of draw it to figure out what's going on, right? Luckily, these aren't too hard to draw. And in fact, they didn't tell you it was in the first quadrant, but you know it's got to be in the first quadrant, because if I do y equals x squared, it looks like this. Right? And if I do y equals 2x, it's going to go here and here. So it's that little piece there. This little bit is the only point of intersection. So I can actually erase the rest of this for right now because I don't want that in my picture. I can figure out the points of intersection very easily just by letting the y values be the same, right? I got x squared equals 2x, so x squared minus 2x equals 0, or x times x minus 2 equals 0 is going to tell you that x equals 0 and 2, which is exactly what we just drew. And this little piece here, which, I mean, honestly, I should have drawn it a lot bigger because you probably can't see it at all. Well, let's try to do a little better job with that. There we go. All right, so it's something like this. And what we're going to be doing is now rotating this around the y-axis. So you can imagine when you rotate this around the y-axis, I'm going to have something. Oh, it's hard to draw the cross section better that I'm doing. I'm not doing a very good job. Right? So it sort of looks like a tulip on the outside, but on the inside, it's got a cone. So if I think about what a regular washer would look like here, again, I'm rotating around the y-axis. So it kind of looks like that. Okay? Now, again, the thickness of my washer is going to be dy. And because I have a hole in the middle, I have to do the outside minus the inside. Okay? So my volume is then going to be pi times the integral, my radius outside squared minus the inside radius squared d thickness. So that's exactly the same regardless, but now I have to figure out which is x and which is y. So my d thickness we said was going to be dy. Now my outside curve is this. Now if I'm going to look at this washer like this, right, the radius is my x. So this is x out minus x in, but I need to actually put it in terms of the y, right? Because I'm going to integrate with respect to y. So I need to solve both of these for the x and plug that in. Okay? So my outer curve is the x squared curve, so that is y equals x squared, or x equals square root of y. And so that would be here, square root of y squared. That's the outer radius. And the inner radius is just going to be the distance to the line. So that is y equals 2x. And if I solve it for x, then I get x equals y over 2. So I want to subtract that, like so. Okay. Remember, so the reason, couple things, the reason I'm changing it to y is because I am integrating with respect to y, so I need all these guys to be the function written as x in terms of y, because the radius here is the distance x. Second thing, don't be confused. Remember, really, we start out with this. And this is the only part that we start out with. And I'm just, when I put it on the other side, I'm just trying to illustrate as best I can this thing where we're going around. Okay? So there is that. Now the last thing I need is the limits. I happen to solve for the x values. Here's 0 and here's 2. But what I really need is the y values that correspond to those. And of course, you can plug them into either of those. If I plug in x equals 2, I'm going to get y equals 4. So my integration limits are from 0 to 4. Okay, so then what do I have? Now I'm all set up. And this integral isn't hard to do. I have y minus 1/4 y squared dy. So that is going to be y squared over 2 minus y cubed over 12. Evaluate from 0 to 4. I'm running out of space. Oh, it's a perpetual problem. Okay, so what I have, 4 over 2 minus, no, not 4, 16. Yeah, so that's better, right? 16 over 2 minus 64 over 12. And if you work that out, it's 8/3. So my actual answer is 8 pi over 3.